Yes, so good afternoon, everyone. This work is basically a development of elastoplastic phase field for modeling fracture in fiber reinforced composites. So the motivation behind this work is basically that composite materials are heterogeneous materials and they show several kinds of non-linearity, for example, because of plasticity and damage, and modeling them is not trivial. So, moreover, people have conducted many experimental tests, but those tests are not adequate so as to extrapolate those properties and propose models for composite materials at mesoscale or, say, the macro scale. Even modeling at the laminar scale requires that we prescribe proper envelopes which are derived from different loading conditions which are applied at the micro scale so that we can properly derive the degradation as well as the envelope for modeling of the mesoscale. So micromechanics basically provides us this virtual testing platform where we use numerical techniques and model the composite material, which in this case is a fiber reinforced composite material. It is GFRP. So it has two phases. One is the fiber and other is the matrix. So we are able to model both of those materials explicitly and find out what their combined behavior is using micromechanical simulations. So micromechanical simulations are of different kinds. So here we have taken help of microscopic volume elements, wherein we take this composite material, we zoom into the microscopic level, and we basically pick up a microscopic volume element. We take a small chunk of this material, and we basically want that material to be representative of how the material is going to behave at the mesoscale, at the laminar scale. The structure of the presentation is basically discussion of the phase field model that has been developed in this context, which incorporates plasticity. And then we will talk about the numerical investigations and discuss the results. The results will be first based on the epoxy specimen because we have the composite material which is composed of fibers, but the fibers are usually they have higher toughness. So we have not modeled the damage of those fibers, and they have been modeled as linear and elastic. But the epoxy specimen has been modeled as plastic and it undergoes damage. So we will, after the development of the phase field model, first discuss those results in the context of epoxy itself, and then we will proceed to the analysis of the microscopic volume element. So these basic equation, and I'm sure because many phase field presentations have been there, so you might be aware of what phase field model is, but I'll discuss it very briefly. So in phase field model, we basically model the crack as a diffused representation of what it in actuality is a discontinuous phenomenon. So here we prescribe the kinematics of the problem, where we assume in this case infinitesimal strain. The strain is thought to be composed of the elastic and the plastic component separately, and we write the equilibrium equation, which is the standard equation. So in this model, what we are going to do is we are going to prescribe these constitutive functions and find out this value of sigma, the stress we are going to prescribe, and then we are going to solve this equilibrium equation and solve this equation. The diffuse crack is represented by, with the help of the crack surface energy function, which we see here written as diffuse crack. So here what we do is wherever the crack will be, there will be some dissipation happening. That dissipation is given in terms of a geometric function, which is given using these two terms. So the first term is this alpha d by c naught L, which gives the geometry of the crack, that it in what way it is diffused over the region where there will be discontinuity. Whereas the second term is responsible for prescribing the gradients of the damage variable. Here the damage variable is d, which is also called the phase field variable. So moving on, we to prescribe the constitutive relationships, we first describe the thermodynamic restrictions. We start by the first and the second laws of thermodynamics, where we say that the stored energy and the dissipation in this continuum is going to be equal to the external power that is there in this body. And moreover, the second law will prescribe that the dissipation has always to be non-negative. The external power is standard. It is the work done, the rate of work done by the external traction and the body force. The stored energy comes from the elastic strain energy. Here, the elastic strain energy is decomposed into these two parts, which is psi naught plus and psi naught minus. So psi naught plus and psi naught minus are usually this is a decomposition which is done on different. There are different methods to do this decomposition. In this case, we have separated the elastic strain energy into the distortional part and the compressive part. So we want the fracture to be driven primarily by the distortional part only. So in this way, we prescribe the stress. This is sigma with this GD, which is the degradation function. So degradation function is responsible for diminishing the value of the strain energy as damage proceeds. Sigma naught is a definition of the effective stress. Effective stress is basically the fictitious stress in the fictitious undamaged material in this case. So so in standard continuum damage mechanics framework, what we have is usually we have the effective stress and we multiply it by some degradation function and we get our true stress, which is sigma. But here the relationship is not that simple. So in this case, what we have to do is when we write the dissipation. Now, recalling that in the previous slide we had described the first part of the dissipation, which was due to the crack. So here we encounter the dissipation due to the plastic flow in the material and the dissipation due to the artificial viscosity. So here we have decomposed the stress, the effective stress in the plastic dissipation into two parts, which is basically a scalar measure of the stress. So here sigma naught was a tensorial measure of stress, but to write the plastic dissipation, we usually prefer to write in a scalar fashion so that we can relate it with the accumulated plastic strain, which is a scalar measure of the plastic strain that we are going to take. In that way, we can write the dissipation due to the plastic flow in the material as dP. So proceeding further, now we have the different functions ready with us. So as I described before, we have the elastic strain energy, which we have decomposed into these two parts, the distortional and the compressive part. The degradation function is usually a standard degradation function. There are other kinds of degradation functions also, but here we have chosen the standard quadratic degradation function. The study is not related to the different degradation functions, but rather to the implementation of this phase field model. The plasticity model utilizes a paraboloidal yield surface criteria, which basically incorporates the effect of pressure causing plasticity in epoxy material. This was given by Sagar in 1971. The, the plasticity potential function also contains the distortional component from the von Mises stress and also from the pressure. So alpha here is a parameter that controls how much dependence on the pressure is there from this model. But these models have already been developed. We are going to implement this into the phase field equation. So now that we have these constitutive functions, we basically substitute them into the laws of thermodynamics and we get the evolution of phase field. So evolution of phase field is usually a very standard equation that we get in usual 81 and 82 type regularizations. Here the only difference is that, so let us look at this equation below phase field evolution. So here we have G dash T multiplied by this the positive component of the elastic strain and the positive component of the plastic dissipation. So usually in phase field, we only have that elastic part, not the plastic part. So this is the only difference that we have until now. But this is not the complete picture because now we are going to implement a damage activation function also. Because in phase field model, what happens is when we are modeling the fracture in a smeared fashion, we basically have to define a range over which it is going to be smeared. So that is given by the length scale. The length scale usually in 82 type modeling and 81 modeling represents a material property because it controls strength of the material when we plot the stress versus strain based on that length scale. But here we want to propose a damage activation function, which is also been observed experimentally in epoxy materials. This damage activation function takes into account both the invariants of the stress. So it is basically an invariant based damage activation. So we basically get a multi stress criteria. so that it is not a constant failure strain or tensile failure strain that we are giving. It's going to be a complete surface. To model this, we basically have this function, the loading function FD, and this is like the damage activation surface. So when our loading reaches that surface, the damage is activated. To implement this activation function, we have used this indicator function, which is IF. So indicator function is activated as soon as the damage is activated. So we modify now the phase field evolution equation in the previous slide. So in the previous slide, we had the driving force, which was Y. Now we have changed it to y multiplied by if, which is very simple. I mean, we are just simply increasing the driving, but we have to keep in mind that even if the activation was not fulfilled, the driving was still there. We were just not activating it. So if we were to use this phase field model as some others have used before, what we would get is, as soon as the damage is activated, we get a sudden increase in the driving force, and we get a phase field that does not smoothly go from a value of 0 towards some finite value. So phase field usually goes from 0 to 1, 1 meaning that the material is completely damaged, and 0 meaning that it is intact. So here, when we suddenly activate this indicator function, we get this driving, and we get a finite value of. So to counter this problem, this numerical problem, basically introduce this barrier, this psi c. So barrier is basically the energy, this driving energy, that is psi naught plus WP naught plus, that will be consumed until the surface is reached. So we basically subtract this so that further whatever driving we get will be responsible for the evolution of the phase field. So once more, we modify this driving force as this final expression of the evolution of phase field variable. Here we only have this psi c subtracted, this extra term. Right. This is implemented totally in Abacus. We have used explicit finite elements implementation of it. We wrote the phase field element in the user element, and the plasticity model in the material model using the view mat subroutine. We use parallel computations using external database subroutine using MPI. So that was implemented in Abacus. So let us now discuss the numerical investigations involved here. So now that we have this model, we first have to, because previously people have not implemented this model in the context of FRPs, and not exactly like this. They have used other kinds of plasticity models or activation functions, or without that even. So we first want to be convinced that how this model behaves in simple problems, only then we will be able to extrapolate this to the MV problem. So we take these two specimens, one for the tension specimen, another for the compression loading. This is a GFRP material that we take. So another note here. So usually another drawback of phase field materials is whatever length scale that we have chosen, the width of the smeared part of this crack, usually that dictates how much strength the material will have when we plot the stress versus strain. But here, since we have proposed an activation function for the damage, so we have basically fixed at what level the fracture should be activated. So wherever sigma reaches its peak. So here the length scale cannot control what the strength of the material will be. So here what we basically do is, instead of calibrating what people usually do, they calibrate the length scale so that they can match the strength. Here we have chosen the length scale which is appropriate for the dimension of the problem. So what we have now done is calibrated the value of the fracture toughness, the material parameter GC, which represents in some way the fracture toughness. It is not exactly that. Usually there are some correction factors there. So we have calibrated this with the local continuum damage mechanics model. The local continuum damage mechanics model was implemented by Melro in 2013, and he used the regularization over the elements using Bazan's crack band theory. So there, the fracture toughness was 0.09. So here, the fracture toughness that we are getting are really lesser than that. So at these lesser value of GC, we get the same material response as the local CDM model. So to calibrate this model, we first have to conduct this tensile specimen test. So we simply apply a tensile load and we see the crack. So the first graph we see are the load displacement plots. So the load displacement plots shows us for different values of GC that as we increase the value of GC, it is able to take more load. But this does not mean that the strength of the material has also increased. So the second graph, which is this figure number C, here we see the stress versus strain plot at a typical element which is damaged for different values of GC. And we see for the value of GC that we have chosen, that is 5e minus 4 Newton per mm, it closely matches the local CDM model. And for higher values of GC, only the softening part is very gradual. So that is the only difference. The strength of the material is fixed, which is unlike the other traditional phase feed models, where the strength itself varies. Here, the strength is fixed because we are using the activation function. So the last graph shows us the relation between the evolution of phase field and the accumulated plastic strain gamma p. So here, this graph is a bit appropriate in this situation because if we see the value of GC for higher values of GC, we see that the evolution of phase field is very less, but the evolution of the plastic accumulated plastic strain is really high. So in those models where GC value was higher than how we had calibrated, you would see very high plastic straining, which is unlike the kind of material that we are trying to model. So another note on this purple graph that we are going to use here. So here also it tries to reach asymptotically to the value of 1 for phase field as the value of gamma p increases. So since we are modeling a brittle fracture here, usually what will happen is once a material is failed and the crack propagates, but phase field is just asymptotically reaching the value of 1. So that material will continue to gain more and more plastic dissipation. Although that is not important as the simulation progresses because the stiffness of that will be degraded so much at that time. So just a note as we move further and see more simulations. So here so here we basically have these 4 sets of contours. The first so we have 3 sets. So the top one is at loading position 1 and then 2 and 3 as the crack is progressing from U1 star, U2 star, and U3 star. So the first set shows us the plastic straining. So we can see that plastic straining is localized here. But what is interesting about this is graph number B and C. So in graph number B and C, we are basically plotting the 2 components of the driving that we have considered in our model. One is the elastic driving and the other is the plastic driving. So the values of the elastic driving are very less as compared to the values of plastic driving. So this is another distinction that we are making, that this is not a brittle phase field model which is driven by elastic driving, but it is driven rather by the plastic part of the driving. So this will be important as it is really helpful to model this failure under compression where shear band formation would be most critical. So the last part of the graph basically shows us the driving with the indicator function. So this basically, as we can see, is very close to the values of the plastic driving, which basically cements the fact that we are mostly considering the values of the plastic component. So moving on, as we have calibrated before in the tensile specimen, the value of GC, all we need to do is we need to verify this for the compression specimen also, because the model of plasticity under tension and compression is different. The strength of material under tension and compression is different. So we need to check those two also. So we get that match here. The load versus displacement plot is very close for both the phase field model for GC 5e minus 4 and the local model that we have. So moving on. So here again, we can see, so again, we have these 3 sets at 3 successive displacements as the crack is progressing. The first one shows us the plastic straining. So compared with the tensile specimen, the compressive specimen usually is able to take more plastic deformation at the initiation of damage. That is because of the hardening data that we have considered. The compressive initial yield at the compressive is much greater than the initial yield at the tensile, and the difference between the initial yield of compression and the strength under compression is lower than the initial yield at tension and the strength under tension. So we will usually see that the compression specimen will show very less non-linearity in its graph, and it will fail very in a very brittle manner as it undergoes slight stage of plastic deformation. So here the second part shows us again the elastic part of the driving, and the third part shows us the plastic part of the driving. Again, we are able to see very high values of plastic driving, which are able to propel the crack in this inclined direction, which is as it is expected from experiments and other numerical results also. It will propagate along these inclined shear bands. So moving on, another study that we wanted to do because we had considered the split of energy using the deviatoric and the compressive split. So there are many other kinds of splits also that are prevalent in phase field literature. That is the spectral split, which is based on the work of Mihe, who basically did the eigenvalue decomposition of the strain and proposed the positive part of the strain energy and the negative part of the strain energy. So interestingly, in this part, we do get the phase field patterns which are along the shear bands, but usually we do not get the evolution that is complete. So that we suspect is because as we are using the damage activation surface, and since the driving is different, so there is considerable amount of stress redistribution happening here, which makes the phase field evolution not imminent. So what happens is, as the damage activation criteria is fulfilled, the material, because of redistribution of stress, basically unloads. So as it unloads, it is not able to fulfill the damage activation successively in the other stages. So in this load displacement plot for the compressive specimen that we see, so this orange one is for without the split, and this dotted one is with the spectral decomposition. So here we see that we do get the pattern, but it does not fail completely. So in the case of without split, even the crack pattern is not complete. So another interesting point to note here is without the damage activation, people have used this with the plastic deformation, and they have usually got unrealistic crack patterns, not even these inclined patterns. So we think that these inclined patterns are only because we are using the stress based damage activation criteria. That is why we are able to get this inclined crack, but it is not representative of the basic phase field fracture that we usually are expecting. So
because your time is over.
okay, it's over. So just uh, give me a couple of minutes. I'll just summarize the MV results also. They're just extrapolation of this.
Yes, you try to conclude because your time is over.
Yes. So we now conducted these tests for the MVs. We have different sizes of MVs, and we took multiple realizations. Here we have taken 4 realizations. So the first and the first part basically shows us the plastic deformation, and the second, third, and fourth basically show the progression of the phase field crack through this MV. So from the first diagram, we can see that the evolution of plastic is basically directly under tension, and we see multiple cracks appearing at different locations, and we see meandering. This is usual crack patterns that we observe in these MVs. So here are the different realizations that we got for all the final phase field patterns. We have all of them having under some 8 to 10% of the strength, the peak stress for all the realizations. Mostly the cracks are perpendicular to the direction of the loading. So for transverse compression, we see the shear bands forming. The first diagram shows us the plastic straining just before the damage. So we can already see that the shear bands are forming along the tangent to the various fibers that we have, and then we see the fracture forming along those tangents. So here we don't see that the crack is meandering around the fibers that as we saw in the tensile specimen, because they are mostly forming along the tangents, which were because of the shear bands. So
sorry, I must stop you on the conclusion, please.
yes, so we did this test for compression and for shear also, and we saw these similar expected results. And we did these size studies also, and we saw that as we increase the size of the MVs, we saw that the standard deviation of the results across the different realizations was diminishing, which is also expected. But in terms of the critical strain, which is the strain at the peak stress, we did not see much asymptotic behavior here, as we can see in the bottom graph of the second column, that it was not asymptotically totally reaching. So we suspect that we will need more larger size of MVs to assess proper critical strain values to be used for laminar level modeling. And so these are just for reference, all the different sizes that we constructed. So these are just one realization.
So if I can ask you, only conclusions, because your presentation is over 25 minutes, only 15 was.
Yes, yes. So
Only
basically,
conclusions.
yes. So the results and the discussions that we have. So basic conclusion is that for modeling these MVs for higher size and for proposing these damage models, for getting the critical strain values which are asymptotically reaching, we need higher MV sizes. And especially for the shear crack formation, we saw some variation wherein there was some direct tensile failure in the principal direction and some multiple sliding failure in horizontal and vertical direction. So in the shear case, we suspect that more realizations are required, and for critical strain, we suspect that higher sizes of MVs are required. So so just a final note, the future work from this would be the development of CDM-based models for laminar level modeling. So we are actually working on these models for having an anisotropic damage tensor using these different simulations. And also we have not discussed that about post-peak homogenization. So here we are considering the stress and strain, which are directly taking the direct average. But usually as we increase the size of the RV, the area of the crack or the damage zone does not increase proportionally. So we cannot take by value the results of conventional direct homogenization. So we are working on that. So thank you so much for your patience.